Hello everyone. In this session, we will study phase shift in star delta transformer. The positive and negative sequence voltages and currents will have a phase shift when it is passing through star delta transformer. The terminals of the transformer are labeled using dot convention. So dot convention indicates that current will be entering from the dotted terminal to the undotted terminal. Let us see. Now this is the star delta transformer, primary star connected, secondary delta connected. Now here the primary side, usually it is high voltage side. The terminals here you see it is represented by capital ABC, and on secondary side, usually low tension side, the terminals are represented by small ABC terminals here. So that is the capital terminals. Capital indicates the high voltage side, the lower case indicates on the lower side. Now let us see here, this is a dot convention, we have used it here. This is a dot convention on secondary side. So which means that the current will be entering from this dotted terminal to the undotted. This is undotted terminal. And at the same time, the windings which are shown parallel to each other are magnetically coupled and are wound on the same core. See now here the winding A to N, isn't it? This winding is in parallel with this winding. So this winding is nothing but this is the terminal A and this is the terminal B. So that means this is AB, small AB, isn't it? This winding is in parallel with this one. So therefore the voltage of this phase and this phase are in phase with each other. So VAN is the phase voltage on star side, will be in phase with the voltage, that is phase voltage on secondary side, that is AB. Similarly, you see VBN is a winding which is parallel to this winding. This winding is nothing but your BC. So VBN, VBC. That means these voltages are in phase and are magnetically coupled and are placed on same core. Now you see this winding and this winding are in parallel. So therefore the voltage across this winding and across this winding are in phase. Is it clear? So that is the meaning of this dotted convention. So using this dot convention, the transformer terminals are labeled. Now using this star delta transformer, now let us construct the vector diagram here. Before constructing the vector diagram, we know from the basics the line voltage on star side is AB. So that is equal to vectorial addition of VAN minus VBN, isn't it? So this is the thing. The line voltage on star side, that is VAB, is equal to VAN, that is VAN minus VBN. So suffix 1 has been given. So first we will treat this star delta transformer with positive sequence voltages. So that's why suffix 1 indicates this transformer, star delta transformer primary is excited with positive sequence voltages. So case 1, when this star delta transformer is excited with positive sequence voltages, so what will be the phase shift? So that is what we are going to learn in this session. Now from this one you see the line voltage VAB is nothing but VAN minus VBN, and 1 indicates it is positive sequence voltages. Now you know how to represent the positive sequence voltages in vectorial form, right? So what is positive sequence? Now this is a positive sequence, so which will have a 3 vectors of equal magnitude and are displaced from each other by an angle 120 degrees. So this is what we have learned in the previous session. So see, phase sequence is A, B, C. So 1 indicates it is a positive sequence voltages. So these are the positive sequence voltages. Now consider these positive sequence voltages as a reference vectors. Now with this reference vector, we are going to represent the different voltages depending on the dot convention which we have represented in this star delta transformer. Now you see VAN, what is VAN? Means it is the phase voltage, positive sequence phase voltage on star side, VAN. Now what is the corresponding phase voltage on delta side? This is the corresponding winding which is in parallel with this one. So what is the corresponding phase voltage here? It is AB. We have to read A because this is a dot convention. The current will be entering this dotted terminal towards the undotted terminal. So what is this voltage across this winding will be VAB. So therefore the voltage across this one is VAN1, indicates it is positive sequence phase voltage on star side. What is the corresponding phase voltage? This is one, that is AB, VAB, and suffix 1 we will represent. So that indicates it is a positive sequence phase voltage on delta side. So therefore positive sequence voltage on star side and positive sequence phase voltage on delta side are in phase. So I am going to represent this vector VAB1, that is VAB1. So this is a positive sequence voltage on delta side across this phase, will be in phase. Similarly VBN, that is VBN, this is this one, this winding. So on delta side this winding is in parallel with this one. So the voltage across this winding and this winding will be in phase. So VBN already we have represented here. So what is the corresponding phase voltage on delta side? It will be the voltage across this winding, that is VBC. So VBC is the voltage across this winding, and suffix 1 we will give for positive sequence. So VBC will be in phase with VBN1. Okay. Now similarly this winding, that is VCN1. So VCN. So this winding is in parallel with this one. So these two voltages are in phase. What is the voltage across this one will be CA, isn't it? CA1. So therefore VCA1 is in phase with this voltage, that is VCN1. So VCN1 is there already. So this voltage will be in phase, that is VCA1 will be in phase with VCN1. So we have represented the voltages on primary side and delta side, and we know that the line voltages is equal to phase voltages on star side. So only the thing is we should get the relationship between line and phase voltages on star side, isn't it? So let us get that vector diagram on star side. Star side we have represented already VAN1, VB1, that means phase voltages. So from these phase voltages let us get the line voltages VAB or VBC or VCA. So let us consider for one phase, that is VAB, let us consider. So we have seen that VAB1 is a line voltage, positive sequence line voltage, is equal to VAN1 minus VBN1. So vectorial addition, these two. So VAN1 vector is available here already. Now we should get minus VBN1 vector. How to get this minus VBN1 vector? Now VBN plus VBN1 vector is available here. How to get minus? So construct the vector which is in opposition with VBN. So that will be this is the vector minus VBN1. Okay. So this is VBN1 minus VB1. So you take antiphase vector. So we will get minus VBN1. Now the resultant of these two, that is VAN1 minus VBN, will be our resultant vector. Now from the basics you know that one. So how to get the resultant? So draw a parallel line here which is parallel to VAN vector, and one more parallel line which is in parallel with VBN, this one. Understood? Now the resultant will be this vector. So this is the resultant vector, that is VAB1, that is positive sequence line voltage. VAB1 is positive sequence line voltage. Okay. Now what is the line voltage on VAB? Means VAB, this is the line voltage. Now what is the line voltage, corresponding line voltage on delta side? It is AB, that means this one, that is VAB, small ab, VAB1. Now here this is positive sequence voltage, line voltage on star side, and you see VAB1, that means VAB1, this voltage. So we have represented here. This is the line voltage or phase voltage. Both are same on delta side. So we will treat it as line voltage on delta side. So positive sequence component of line voltage on star side and positive sequence line voltage on delta side. Clear? Now between these two line voltages on star side with respect to delta side, now what is the angle we are having? This will be 30 degrees. Okay. So therefore from this one, how we can write? VAB1 is lagging behind the star side quantities, or the star side quantities will be leading with respect to delta side quantities by 30 degrees. In either way you can represent it. So therefore from this one, so we can represent this VAB1 is equal to, so VAB1 at an angle of, because it is leading by 30 degrees, VAB1 is leading the VAB, this VAB1 by 30 degrees. So represented by VAB1 at an angle of 30 degrees and multiplied with X. So where X is phase transformation ratio. So this is a relation we have obtained from this vectorial diagram, that is resultant vector is leading with respect to the, that is star side component is leading with respect to the delta side components. So that means, now this is the conclusion. The positive sequence line voltage on star side, what is that one? VAB1 leads the corresponding line voltage on delta side. So what is the corresponding line voltage on delta side? VAB1 by how much angle? 30 degrees. So that is a conclusion we can draw it from here. That means line voltages on star side leads the line voltages on the delta side by an angle 30 degrees. Now this holds good even for line to neutral voltages on two sides and also applies for line currents. Here we have taken line voltages. This same expression also holds good for your line currents. Now this analysis we have made when this primary side of star delta transformer is excited with positive sequence voltages. That's why we are given suffix 1. So from the overall analysis we can say the star side line voltages, positive sequence components of line voltages on star side leads the line voltages, positive sequence line voltages on delta side by an angle 30 degrees. That is the conclusion we have drawn it here, and the equation will be represented in this form. Okay, now let us see the same star delta transformer when it is excited with the negative sequence voltages. So for negative sequence voltages we are going to give suffix 2, isn't it? So the same relations holds good. So only the difference is when star delta transformer is excited with negative sequence voltages. So what will be the equation? Now let us consider the negative sequence components. Now you know how to represent the negative sequence components. The phase sequence will be in reversal order as compared to the positive sequence. So this will be ACB. Earlier in positive sequence this was ABC. Now it is ACN. So VAN2, suffix 2 indicates it is negative sequence components. What is VAN2? VAN is a phase voltage on star side. Again VBN is another phase voltage and VCN is again phase voltage. So 2 indicates it is the negative sequence voltages. So when the primary is excited with negative sequence voltages, so this is the reference vector diagram we have drawn. And with respect to this vector diagram, now let us represent the corresponding voltages on delta side. Now what are the delta side? Now you see AN, and here parallel winding is this one, that is AB, VAN and VAB. Now here you can see the same thing holds good here. So VAB2, only the difference is suffix 2 I am using it here. Is it clear? Suffix 2 I am using it. So VAB2 are in phase. Similarly VCN, that is VCN. What is the parallel winding for this one? So this one, that is VCA. So VCA and VCN2 are in phase with each other. Similarly, VBN, so VBN2, that is negative sequence phase voltage on star side. And what is the corresponding parallel winding here on delta side? This winding. So what is the voltage here? It is BC. So VBC2 will be in phase with VBN2. Is it clear? So we have represented voltages on star and delta side. Same way I have explained in the previous slide. Here also, let us take the relation between line and phase voltages on star side here. Now VAB, now let us take VAN minus VBN, isn't it? Same relations as we have discussed in the previous slide. What is VAB is equal to VAN minus VBN. Suffix 2 you indicate it. So VAN2 minus VBN2. So VAN2 vector is available here, minus VBN we need. So where is VBN plus VBN2 is available here, but we need minus VBN2. So take a antiphase vector to this VBN2. So this is the vector which is in antiphase with V plus VBN2. So that will be your minus VBN2. So vectorial addition of VAN2, that is this one, and VBN2. Vectorial addition of these two will be resultant line voltage AB, isn't it? So let us see how to get this resultant one. So draw a parallel line. This will be parallel to VAN2. From here another parallel vector to this one. So this one. So therefore resultant vector will be this one. So what is this resultant vector will be? VAB2. Now you see here from this vector diagram it is clear that what is VAB2 AB. So we can treat that one as either line voltage or phase voltage. Now here what is this VAB, capital AB2 VAB? It is nothing but line voltage on star side. Now what you can conclude from this vectorial diagram, what you can conclude, what is the relation between line voltages on star side and delta side? You can see here the negative sequence voltages, negative sequence line voltages on star side is lagging behind the corresponding line voltages on delta side. So which is, so what we have seen in positive sequence, it was leading. So now here it is lagging. So therefore here VAB2 is lagging behind this V small ab2. That means these are the star quantities and this is your delta quantities. So star quantities are lagging behind the delta quantities. So from this one, this is by 30 degrees. Now, so how to write VAB2 is lagging. So therefore VAB2 of minus 30 degrees. So where X is phase transformation ratio. So from this one what we can conclude, the negative sequence line voltage, on star side lags the corresponding line voltages on delta side by, so this is lagging by VAB2 by an angle 30 degrees. Is it clear? So that is the thing. So when this star delta transformer is excited with positive sequence voltages, this will become reverse. That means what? The positive sequence line voltages on star side leads the corresponding line voltages on delta side by 30 degrees. Is it clear? When it is excited with negative sequence voltages, then it lags. Star side quantities lags delta side quantities by 30 degrees. So this is what you should remember. So this is the phase shift which will undergo. Now let us see another example. So the star side quantities leads the delta side quantities. So when the star delta transformer is excited with positive sequence voltages, right? This is what we have studied. Second case, what we have studied, when it is excited with the negative sequence voltages, star side quantities lags the delta side quantities by an angle 30 degrees. This is what we have studied. Please keep it in mind. However, this depends on the labeling of these terminals. Now let us take this example. So this is a star delta transformer. This is case 3, you can assume it. So this is star side, we have not changed anything. On delta side, the terminals are named it in different way. So earlier these terminals are named it as this is A, this is C and this is B. Okay, now here it is named it as CBA. So it is different terminology, we have labeled it in different way. So even if you change the labeling of the terminals like this, so the lagging and leading, the star and delta side quantities will vary. Now let us analyze with this terminals. Star side we have not changed, only on delta side the labeling of the terminals just we have interchanged. Earlier it was different and now it is CBA. Now let us take it for positive sequence. When the primary side is excited with positive sequence voltages, so we will have the positive sequence voltages as a reference vector. Now consider we have not changed anything on primary side, so it will remain same, similar to our previous case 1. Okay, so here you can see VAN1, VBN and VCN. VAN, VBN and VC. Phase sequence is A, B, C. 1 indicates it is positive sequence. Is it clear? So that means it is excited with primary is excited with positive sequence voltages. Now let us see. VAN is a phase voltage. What is the corresponding phase voltage or winding which is parallel to this winding on delta side? So this is the winding on delta side which is parallel to this winding. So this voltage drop and this voltage drops are in phase. What is this voltage drop is? VAN1, positive sequence voltage. What is the voltage now here? You see VC, you cannot read VAC because from the dot convention. So CA, isn't it? This is the CA. That means VCA is the voltage, phase voltage. So VCA is in phase with this voltage. So here you can see VCA 1 indicates positive sequence component is in with VAN1. Now VBN. Now can you tell me which winding is in parallel with this winding? Is this one, right? So this one means what is the voltage? VAB. So VAB will be in phase with VBN. Now these two. Now you see VAB1 is in phase with VBN. Similarly VCN, isn't it? So this winding parallel to this one is this one. So VCN and VBC. VCN and VBC are in parallel, in phase. Is it clear? So we have represented line voltages on star side and line voltages on the delta side. Now let us get the resultant vector on star side, line voltages and phase voltages. Now as usual VAN1 minus VBN we have taken in the earlier case. Now you see here, what is the line voltage? VAB. What is the corresponding line voltage? Here it is VAB, isn't it? The corresponding line voltage is, here it is VAB and this is line voltage. But what is the vectorial addition here? You see this winding, VAB is this winding. First winding is coming here, isn't it? So this winding is in parallel with this one, isn't it? So what is the corresponding line voltage? AB on this one is AB. But when you consider this one, this winding is in parallel with this winding. So therefore, if we want to get the line voltage, we have to read that VBA. So that means what? VBN minus VAN. So VBN minus VAN. So we are going to get, that is the line voltage we are going to read. Earlier case 1, we have read VAN1 minus VBN1. But here the corresponding line voltage on delta side, this winding VAB, so is in phase with this winding. So we have to read from this direction. So therefore VBN minus VAN is equal to the resultant vector between the lines A and B we are going to get. Now let us see here. So what is this one? VBN minus VAN. Where is VBN? VBN vector is here. VBN1 minus VAN. Minus VAN. Positive VAN1 is available here. Minus VAN1 we should get. So construct the vector in antiphase with plus VAN1. So this is a vector in opposition to plus VAN1 is called as minus VAN1. Resultant of VBN1 plus VAN, that is vectorial addition of VBN1 plus of minus VAN1 is your resultant line voltage. As usual, construct parallel line, then this is a parallel line, this will be your resultant VBA1. So VBA1, so therefore VBA. Now you see here again you have the phase difference of 30 degrees. Now can you tell me the relation between what is VBA1 is the line voltage on star side, VAB1, what is this one, is a line voltage on delta side. So line voltage on star side and line voltage on delta side. What is the relation here? Line voltage lags the line voltage on delta side by 30 degrees. That is, the line voltage on star side lags the line voltage on delta side by an angle 30 degrees. So this is what we can write it, that is VAB1, small VAB1 is equal to X VBA1. So X VBA1 of 30 degrees, where X is the phase transformation ratio. So this is where this one is X is phase transformation ratio. So this is a relation, we got it there. Now let us see the positive sequence line voltages on delta side lead the corresponding line voltages on star side by 30 degrees, isn't it? So it is in opposition. So first case 1 we have seen when it is excited with positive sequence voltages. Case 2 we have seen when it is excited with the negative sequence voltages. Case 3, now this is case 3 what we are analyzing. It is excited with positive sequence voltages, only the thing is the labeling of terminals on delta side has been changed. So when it is labeling of terminals has been changed, what will be the effect? So we have seen here. So this is excited with case 3 and case 1 are similar, both are excited with positive sequence voltages, only the difference is labeling on the secondary side is different. So in this case 3, the positive sequence line voltage, what is the positive sequence line voltage on delta side? VAB. What it is leading the corresponding voltages VBA1, that is line voltage on star side by 30 degrees. Is it clear? So the positive sequence line voltages on delta side, this one, is leading the corresponding line voltages on star side. Corresponding line voltages on star side is this one by an angle 30 degrees. Whereas case 1, same thing, it is excited with positive sequence voltages, but the terminals are represented here as A, C, B. There it was in reverse. The positive sequence line voltages on star side leads the corresponding line voltages on delta side by 30 degrees. That is case 1. Now case 3, it is in reverse way. Understood? So in simple way, final conclusion, when the star delta transformer is excited with positive sequence voltages, case 1, what happens? The positive sequence line voltages on star side leads the corresponding line voltages on delta side by 30 degrees. Whereas when the star delta transformer case 2 is excited with negative sequence voltages, then what happens? The negative sequence line voltages on star side lags the corresponding line voltages on delta side by an angle 30 degrees. And this is different scenario I have explained. So therefore it depends on the labeling of the terminals also here. Is it clear? So this is regarding the phase shift. That means whenever the star delta transformer is excited with either positive or negative sequence voltages, will have a phase shift. Is it clear? Thank you.